The Large Hadron Collider, LHC, the world's most powerful particle accelerator, has pushed the boundaries of human knowledge, unraveling some of the deepest mysteries of the universe. Located at CERN, the European Organization for Nuclear Research, the LHC is a 27-kilometer-long ring buried deep beneath the French-Swiss border. Since its activation in 2008, it has been instrumental in confirming the existence of the Higgs boson and continues to explore the very fabric of reality. The journey to building the LHC was decades in the making. The idea of a powerful particle accelerator capable of colliding protons at nearly the speed of light emerged from the necessity to test the standard model of particle physics. Physicists had long theorized about the existence of fundamental particles and forces governing the universe, but direct evidence remained elusive. The LHC was envisioned as the tool to provide this empirical proof, answering questions about dark matter, antimatter, and the origins of the universe itself. The need for such a collider arose as previous experiments, such as those conducted at Fermilab and earlier CERN accelerators, reached their technological limits. Scientists required higher energy collisions to probe deeper into the subatomic world, leading to the proposal of an unprecedented machine. Funding, international collaboration, and cutting-edge technological advancements were all necessary to bring this vision to life, making the LHC a global scientific endeavor. The LHC is a complex feat of engineering, consisting of thousands of superconducting magnets, cryogenic systems, and high-energy detectors. At its core, it accelerates protons within its circular tunnel using powerful electromagnets cooled to -271.3 degrees Celsius, colder than outer space. Once accelerated to near light speeds, these particles collide at designated points within massive detectors, such as ATLAS and CMS. These collisions generate conditions akin to the moments after the Big Bang, allowing scientists to study particles that existed only in the earliest moments of the universe. Each collision produces a cascade of subatomic particles that are carefully analyzed. The detectors, each the size of a multi-story building, are equipped with millions of sensors designed to track and measure the properties of these fleeting particles. This process generates an immense amount of data, requiring sophisticated computing networks to sift through the information and identify meaningful results. The ability to recreate and analyze these collisions is what makes the LHC a cornerstone of modern physics. One of the most significant breakthroughs at the LHC came in 2012, when scientists confirmed the discovery of the Higgs boson, often referred to as the God particle. The Higgs field, which this particle represents, is responsible for giving mass to other particles, a cornerstone of the Standard Model. Before this discovery, the existence of the Higgs boson was purely theoretical. The confirmation of its presence solidified our understanding of how fundamental forces and particles interact, earning François Englert and Peter Higgs the 2013 Nobel Prize in Physics. The discovery was not instantaneous. It required years of accumulating and analyzing data. The Higgs boson is incredibly unstable, decaying into other particles almost immediately after being produced in a collision. By tracking these decay patterns, researchers were able to confirm its existence. This monumental finding not only completed the Standard Model but also opened doors for new physics beyond it. While the Higgs boson was a landmark achievement, the LHC's mission is far from over. Researchers are probing deeper questions, such as the nature of dark matter and dark energy, two components that make up 95% of the universe's mass-energy content but remain largely mysterious. The LHC is also investigating supersymmetry, a theoretical framework suggesting that every known particle has a yet undiscovered partner. If proven, this could provide a pathway to understanding the unification of forces, a long-sought goal in physics. Scientists also aim to resolve discrepancies between the Standard Model and observed cosmic phenomena. For example, the imbalance between matter and antimatter in the universe remains unexplained. The LHC experiments hope to shed light on this asymmetry, potentially revealing unknown physical principles that governed the early universe's development. Another frontier being explored at the LHC is the possibility of extra dimensions beyond the three spatial dimensions we perceive. Some theories, including string theory, propose additional dimensions that could explain inconsistencies in particle physics and gravity. By analyzing particle collisions, scientists hope to detect signs of these hidden dimensions, which could revolutionize our understanding of the universe's structure. One method involves the search for microscopic black holes, which could indicate the existence of extra dimensions. If such phenomena were observed, they would provide direct evidence supporting theories that extend beyond our conventional understanding of space and time. Despite its groundbreaking discoveries, the LHC faces significant challenges. One of the primary issues is the vast amount of data generated. Petabytes of information must be analyzed to identify rare particle interactions. Additionally, higher energy levels are required to uncover new physics beyond the standard model. To address these challenges, CERN has been planning the High Luminosity LHC, HL-LHC, an upgraded version set to begin operations in the late 2020s. This enhancement will increase collision rates, enabling more precise measurements and the potential discovery of new particles. Future upgrades may also include a successor to the LHC, such as the proposed Future Circular Collider, FCC, which would dwarf the current facility in size and energy capabilities. If realized, this new collider could take humanity even deeper into the unknown, uncovering secrets of the universe that remain hidden. The impact of the LHC extends beyond theoretical physics. Its advancements in computing, data analysis, and superconducting technologies have applications in medicine, engineering, and space exploration. Techniques developed at CERN have contributed to medical imaging technologies, improved materials science, and even innovations in artificial intelligence. In particular, particle acceleration technology has found uses in proton therapy, a form of cancer treatment that precisely targets tumors while minimizing damage to surrounding healthy tissue. Additionally, CERN's pioneering work in data management led to the development of the World Wide Web, demonstrating how fundamental research can drive technological progress across multiple fields. The Large Hadron Collider stands as a testament to human curiosity and ingenuity. It is not merely a machine but a gateway to understanding the fundamental nature of reality. With future upgrades and continuous research, the LHC may one day answer some of the universe's most profound questions, ushering in a new era of scientific discovery. As we stand on the precipice of new breakthroughs, the LHC remains our most powerful tool in unraveling the secrets of the cosmos. The story of the LHC is not just about particles and collisions, it is about humanity's relentless pursuit of knowledge. It represents our drive to push beyond the boundaries of what we know, to explore realms of physics that may one day redefine our understanding of existence itself. As the next generation of scientists and engineers continues this journey, the discoveries made at the LHC will undoubtedly shape the course of science for decades to come.